Hey guys, welcome back to another one of these A-level maths statistics videos. Finally, we're on what I promised a while back. We're on binomial hypothesis testing, which is probably one of the trickiest parts of AS statistics. So as soon as we get through this, things will get a little bit easier. So I thought we would just do it just by essentially doing, because this can be kind of difficult to actually explain. So I think it's best to just learn by doing. So if we have a look here, the discrete random variable x is modelled by, that's what this little wavy tilde means, is modelled by B for binomial, so this is a binomial distribution. There are some other types of distribution you may come across, for example a normal distribution, and that would be a capital N instead, so N for normal, B for binomial. And binomial distributions are always written like this. Okay. Now, N is just the size of the trial. So this could be kind of a population size or how many times you do it. So you can just say it's the trial number. This will make a lot more sense as we go through a few more examples, I promise. And this P is probability of failure. Okay. Now the key thing to think about here is sometimes they ask you to use an appropriate distribution. Now of course at the moment we only have binomial distributions, so the only appropriate one is binomial. But for those of you that have already gone a bit further ahead, or when you finally get to things like normal distributions, you need to be able to choose what, choose what you need, right? Choose which distribution. The by part of binomial means 2, so essentially this can only be used if there is only 2 outcomes, which you can broadly call success and failure. You can call it that broadly, okay? And you also need to know the number of trials, n, and you also need to know the probability of failure or success, because then you can just do 1 minus it for failure because there's only 2 outcomes, okay? Now, how do we do this? Well, it's actually not too tricky. We do the whole thing on the calculator. Now, for now, this isn't going to be too tricky. However, it does get tricky, because what you do in the calculator, if it's equal to, okay, so if you see the equal sign, you're going to go to mode, and again I'd recommend you get this kind of calculator here, the FX517991X. I'll make it a bit bigger for the purpose of this lesson. You're going to go to menu and you're going to press option 7, or you can navigate there, which is distribution. Press equals, and here you have your normal distributions, you have your inverse normal distributions, which you won't use in statistics for now, and then we have the binomial ones. Okay. Now you want to look for binomial PD. PD stands for probability distribution, and this is what you use if you have an equal sign. Okay, so I'm going to write that down. Equal sign means you use the PD option. Okay, so in this case we're going to pick option 4, binomial PD. Now you have 2 options, list and variable. Now in most cases you get given a variable, so you get this kind of thing here. List is a bit trickier, and essentially it's what you use if you are searching for a specific value. Okay, we're going to use list a bit later on when we do hypothesis testing, but if when we want to find critical regions, basically you use list in order to find a list of all of the different probabilities, okay, which can be useful in certain questions. So it might say, for example, find the value of x when the probability is 0.617 or something. That could happen, but for most cases, 99% of the time, you're going to use the variable function, okay? Press 2 for variable, and now you're filling in x, n, and p. Now, n and p are just the 2 values in the b part. So in this case, we have n here, and we have p here. And x is just whatever this value is, okay, in the actual distribution itself. So x in this case is going to be 5, you press equals. N is 15, equals, and P, the probability of, again, success or failure, is 0.35. Press equals, nothing happens yet, press equals again, and we get our actual probability. And normally they want you to give it to 4 or 5 decimal places, so because it didn't specify, I'm just going to give it to 4 to make my life a bit easier. So 0.2123. 0.2123. Perfect, okay? Now, what about when it has a less than sign? Well, if it has a less than sign or a greater than sign, you're going to use the CD option. Okay? So again, this is if it has less than, greater than, less than equals, or greater than equals. And they've actually given us a slightly tricky one to start with, because with the next option that I'm going to show you, so we're going to go 7 and go down 1, binomial CD, the C stands for cumulative distribution. So it means add up all of the probabilities up to a certain number. So the way it would work in the bottom case, I'm actually going to do part C first because I think it makes more sense. Okay, it's going to take the probability that x is 0 and the probability that x is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and add them all together. So it's the probability of either 10 or fewer of these things happening. Okay? Now, here's the key thing to remember. Your calculator only ever works like this. It's less than equal to whatever the other number is, right? So whatever number it happens to be. So when we have x is less than 4, we actually have to work out in our calculator x is less than equal to 3, because less than 4 is less than equal to 3. So when I go to variable now, x is not going to be 4, it's going to be 3. And everything else stays the same, so I can press equals twice, and I get 0.1727. So 1727. Oh, that was tricky for some reason. And then for the next part, again, I'm just going to press equals to go back. And the next one is 10 because it is actually less than equal to, okay? So 0.9972 to 4 decimal places. So that's the kind of basics covered, okay? So unfortunately it does get a bit more tricky than this, but this is the basics of what we're going to do. We're going to continuously use this function on our calculator in order to work out different probabilities and use them in questions. Now, remember how I said I recommend this calculator? The reason for that is the alternative is you have to look up the probability tables which they get given you in a data sheet. But there's about 10 pages of them, and scanning through that is very tedious. So I'd recommend just using a calculator, okay? But technically you can use the large data sheet that you get given, or the little booklet you get. But again, this is the basics of what we're going to do. This basically covers binomial, so discrete random variables, and hypothesis testing. It covers all of that, okay? And all we're going to be doing is doing this. However, we use different contexts, which is where things get a bit trickier, okay? So if we go to the first question, the probability of Harry being late for school is 0.1. Over a term of 30 days, find the probability that Harry is late 1 time, more than 4 times, less than 3 times. So the first thing we need to realise is that we can use a binomial distribution. Why? Because there are 2 options. He's either late or not late. Okay? So I'm going to say that this probability can be modelled as a binomial distribution, so B. Now, what's the number of trials? Well, it's a 30-day term, apparently. Okay? And the probability of him being late is 0.1. Okay? So we'll come on to hypothesis testing in a second. So, that's going to be our binomial distribution for now. There are 30 trials, because it says there's 30 days, and the probability of being late is 0.1. So exactly 1 time means you're looking for the probability that x equals 1. So again, hopefully that clicks into your mind that you're going to be using binomial PD, so probability distribution, because again, it's an equal sign. So we're going to be using PD. Okay. Then again, we're going to use variable. So here, x is exactly 1 time. And n is 15, so in this case it's going to be 30 because there are 30 trials. And the probability of, again, successful failure is 0.1. And that's 0.41413, so we'll stick with that. it should also be noted that the normal rules of probability stay the same. So for example, it can never be more than 1, ever. And it can't be less than 0. So more than 4 times. So this is actually quite interesting. What they're looking for is the probability that x is greater than 4. Okay? Now again, I told you that it only goes less than equals to. So what I like to do is I actually like to draw a little bit of a number line. So if I draw the number line, we have, let's say, 0, 1, 2, 3, 4, 5, and 6. Yeah. So if I want the probability that it's greater than 4, okay, and my cumulative distribution only goes up from 0, okay, so it goes into this region, so it will go something like, well, I mean, technically it would be this. Then in order to work that out, what I need to do is do 1 minus the probability that it's 4 or less. Okay, so basically I'm going to be doing 1 minus the probability that x is less than equal to 4. Because again, remember, we're not including 4. Okay. I hope that makes sense. In this case. Okay. So what we need to do is again do 2. So it's 2 steps, but again it's not too tricky, hopefully. So we're going to press equals, and we're going to go back actually, and we're going to do cumulative distribution. So CD variable x in this case is going to be 4, and 13 0.1. So it does carry over, which is quite nice. Right, so this actually carries over. I only entered the x, I didn't enter N or P, but make sure you check it anyway. That's 0.8245. So we have 1 minus. Now, I know what you're going to say, it's a bit tedious to try and type this in, but what you can do is once you have that value, go to menu, press the number 1 or go over to calculate, and then do 1 minus answer, and it will give you your value. And then again, 4 decimal places, so 0.1755. So hopefully that makes sense. For the next bit, it says less than 3 times. So again, you need to read this very carefully. It's looking for less than 3. So what we need to do is actually work out less than equal to 2. Because again, we can't just work out less than 3. It only goes less than equal to for our calculator. So what we need to do is once again, go to menu, option 7 for distribution, and then we're going to go to binomial CD variable. It should also be noted that you could technically just work out x equals 0, x equals 1, and x equals 2 and add them all up. And you'll get the same answer because that's what your calculator is doing. But I'm not exactly sure why you'd want to do that. It would be very tedious. And then we have 30 and 0.1. Cool. And that's 0.4114. Okay. Not too bad, hopefully. Okay. Perfect. So, if we go to the next question now, we have this. This is basically the most complicated that it can become in terms of everything before hypothesis testing. We need to find the probability that 3 is between x and 7. And the distribution we're using is 1. Okay. Again, I would recommend personally using a number line. So if we just do again 0, 1, 2, 3, 4, 5, 8, 8. The values I'm looking for, right, is 0 up to and including 7. So I'm about to get onto that in terms of using the calculator for hypothesis testing. It's literally part B and C for this. Okay? So it's going to come up in a second, I promise. So, in order to work out this, again, remember, we can only go left to right from our calculator. So what we're going to do is we're going to work out all of the values up to and including 7, and we're going to subtract all of the values up to and including 3. Okay? So, what we're going to do, just to make this clear, this is equal to the probability of x being less than or equal to 7 minus the probability of x being less than or equal to 3. So we need two values in this case, and subtract them. So what aren't you sure about? You did join part way through, so it might make it a bit tricky. Okay. So in the meantime, binomial CD, and again we're just entering in the values. So x is 7 in this case, n is 20, and p is 0.41. And that gives me 0.3804. And minus, and we're going to do the exact same thing, but for 3 instead. Zero point 0.0128. Okay, so just rounded both of them to 4 decimal places. What we're going to do, go back to calculate and do 0.3804 minus answer. You get 0.3676. Okay. Perfect. So again, when you're trying to work out the probability of it being between two values, I'd recommend using a number line. So this is what it would look like on a number line for the question. And then you have to realize that your binomial distribution only goes from left to right. So you need to take all the values up to 7, all of the values up to 3, and then subtract them from each other. And that will stop it from overlapping. Okay. Part B is the first hypothesis testing question we're going to do. So as you can see, there are 5 marks. They're pretty big questions. So it says, previous research by a restaurant found that 30% of customers will order a starter. On one day, a random sample of 40 customers is taken and 7 order a starter. Test at the 5% significance level whether the proportion of customers ordering a starter has decreased. So, what is hypothesis testing? Well, if you think about what a hypothesis is, it's a statement. Okay, so the statement here is the proportion of customers ordering a starter decreasing. Okay, but all it means is we are testing to see if this proportion, this percentage or probability, has changed, or in this case has decreased. And hypothesis testing allows us to actually make this test. Okay, so they give you a few different things in terms of what the hypothesis testing is about. So they first give you a probability. 30% of customers will order a starter. Okay, so that probability is 0.3 as a decimal. Okay, and they give you a sample of 40 customers and 7 ordering a starter. Okay, so I can write this as a binomial distribution. Either they order a starter or they don't. So I'm going to say that it's B, 40 customers at 0.3. Okay, so here's how hypothesis testing works. Okay, the first thing you do is you state what your null hypothesis is. So, null hypothesis, what is it? It is the hypothesis that is established to be true. Okay, so there's the hypothesis that is established to be true. Okay, so in this case, can you see that the probability is 30%, and that's established from what it was, right? They've said that previous research found it's 30%. We're testing to see if that 30% has changed. So the null hypothesis, the hypothesis if nothing has changed, is that the probability is still 0.3. And this is actually the probability we're going to assume to be true. Okay? Just as a reminder, you first define your null hypothesis. This is what the probability is established to be true. Okay, so if you look here, they've already said that it's 30%. That's known, it's established. Okay, so that's your null hypothesis. You next need to choose your alternate hypothesis. So if the null hypothesis is wrong, then you are going to accept whatever your alternate hypothesis is. And the alternate hypothesis is whatever you're testing. So you can write P. Now what it says is whether the proportion of customers ordering a starter has decreased. So we're testing if it's less than 0.3. You need to be very careful when you read the question, okay? 30% order a starter, we're testing if the percentage of people ordering a starter has decreased. Okay? Perfect. So far, I'm hoping that makes sense. The null hypothesis is what's already been established to be true. Alternate hypothesis is what you're testing if it's decreased. Okay. Now, they give me a random sample of 40 customers is taken and 7 order a starter. So what you need to do now is using the significance level. This significance level is fairly interesting. The sig level, I'm going to call it. It's 5%, which I'm going to write as 0.05. Okay. I'll show you what the significance level is in a second. But here's how you do the question. It's 5 marks. 40 customers is taken, 7 order a starter. So I'm going to work out what the probability of 7 or fewer people ordering a starter is. And the reason why I'm going to write this down first. So, what am I actually doing? What this means is that I am taking the probability, right, that 7 or fewer people have ordered a starter. The reason for that is I'm testing whether the proportion has decreased. So I'm going to see how likely is it that if my current probability is true of 0.3, that I would have 7 or fewer people ordering a starter out of a sample of 40 people. How likely is that? Okay. So again, this is a very difficult topic to understand. I can show you the method and you'll be fine, but we need to understand it to make it easier, and sometimes they throw, curveballs at you. So just as one more time. This probability I'm working out is the probability that 7 or fewer people ordered a starter, assuming my null hypothesis. Now, if this number's really small, then it's really unlikely for it to have occurred. So it's more likely that the probability's actually decreased, right? So, in your menu, distribution, binomial CD, variable, x is 7, n is 40, probability is 0.3, and we get 0.05528, right? So what that means is basically there is a 5.5% chance that this happened because of this distribution. Okay. So what's the significance level? Well, if you notice, this number is above the significance level, right? It's above the 0.05. So, because it's more than 5%, and this is something we define, there is not enough evidence to support the claim that the proportion of people ordering starters has decreased. Yeah? That's a sentence that you'll just learn to memorize, okay? So what is the level of significance? Okay, the level of significance is a percentage that you decide, right? It's a probability that you decide yourself. And if your probability is below that, it means you're going to say, okay, it's actually more likely that the alternate hypothesis is true. Okay? We're saying that there's only a 5.5% chance that this happened naturally because of this distribution. We're saying that's good enough. That's okay. Right? Part C actually says, what happens if it was a 10% significant level? What would you say? Well, if it's a 10% significance level, then all of a sudden my 5.5% is less than 10%. So what I'm going to say now is the complete opposite. There is, so we would accept H1, right? Because there is enough evidence. Okay? So it's a bit arbitrary in that sense, that you just decide yourself. But what you're basically saying is, if there is a more than 5% chance that this happens because of this distribution, then I'm going to say the distribution's fine. It's okay. In this case, we're saying, okay, if there's above a 10% chance of this happening naturally, then that's okay. My distribution's fine. Does that make sense? So I hope that makes sense. And for those of you that have just joined, we just went through a hypothesis testing question. And we basically tested if the probability is lower. So if you need me to go through that one more time, I'm more than happy to. It's a very tricky topic, but as we practice more and more, you will get a lot better at it very, very quickly. Okay? Because it is a bit of a jarring topic. Okay. Next, the discrete random variable x is modelled by the binomial distribution with a 30 sample size and a 0.58 probability. Part A simply says, find the probability that x is greater than or equal to 12, but hopefully you should know that we can't work that probability out directly. Remember, when you use your cumulative distribution, it only goes less than equals to 12. Okay? So again, you can draw out a little number line just to like test it. So 8, 9, 10, 11, 12, 13. So I want the values greater than and including 12, but my distribution only goes from left up. So what I'm going to do is take all of the values up to 11 and subtract them away. So this is the same as doing the probability of x 1 minus the probability of x being less than or equal to 11. Okay? So let's work that out. So we have 1 minus, and now we're going to go back to our calculator. Again, I would thoroughly recommend you get a calculator exactly like this one, because it'll make your life a lot easier. So x in this case is 11, is the number we're actually testing. Capital N is, in this case, 30. And the probability is 0.58. And that's 0.015 blah 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 blah. 15. Now again, you can just use a little trick to go menu, go back to calculation, which is option number 1, and do 1 minus answer, and you can get your actual value. And I'd recommend doing this to 4 decimal places, because that's what they tend to ask you for. So 0.9849. Okay. Any questions about that so far? I think that's okay. So, for part B, they give us a hypothesis testing question. Okay. So what it says is a cafe expects 30% of customers, so in other words, the probability is 0.3, to order a coffee with their breakfast. On one particular day, a random sample of 40 customers that ordered breakfast is taken, and 19 of them ordered a coffee. And it says, test at the 1% significance level whether the proportion of customers ordering a coffee had increased. State your hypotheses. This actually gives you 1 mark, just writing the hypotheses. So, the null hypothesis, I'll go through this again, is the kind of pre-established probability. It's the one that we already know is true. So if I have a look at this, they expect 30%. So the null hypothesis is that they're right, that the probability is 30%. You then need to define your alternate hypothesis. So if they're not correct, what's the case? If the probability isn't 30%, what is it? Well, they want us to test if it's increased specifically. So that the probability is greater than 30%. Okay? Now, the sample of 40, so I'm going to now write out my binomial distribution. The sample is 40 and the probability is 0.3. And out of that sample, 19 ordered a coffee, right? So we just do 19. So now I'm going to do my actual hypothesis test. Okay? This has already gotten me marks in the exam. Now, what I want to test is what is the probability that 19 or more people ordered a coffee with their breakfast using this model that we have pre-established. So if they're correct and it's 30%, what's the probability that 19 or more people ordered coffee? Why is it more? Because I'm testing if it's more than 30%. Okay? So, the only way I can do that is by doing 1 minus the probability that x is less than or equal to 18. And again, you can use your number line to verify y. Okay? So let's do it. Equals menu, go down to 7. And again, we're not using binomial PD, we're using binomial CD, the cumulative distribution. Go option 2 for variable. X is 18, n is 40, and the probability is 30%. And we get 0.9852. So I'm rushing through it because I'm going to kind of use the calculator to work out what that is. 1 minus, so ... Again, we're going to use menu, go to option 1 for calculate, we're going to do 1 minus answer. So for those of you that have just joined, if you're unsure about any of this, just let me know, because you're joining in halfway through a hypothesis testing question isn't easy. But you're going to get 0.0148. So in other words, that's 1.48%, right? Same thing. Okay, so the question is, what does this mean? Well, if we look at our significance level, which was 1%, right? 1.48% is bigger than our significance level. So, what we can say from this is, so again, what the significance level is, I'll go through it one more time. It's a bit obscure, but it's basically like a threshold, right? So what I'm saying is, if the probability that this has happened completely naturally, using my model, then I'm going to say the probability hasn't changed. There's not enough evidence to say that the probability's changed. Okay, and that's literally what you'd write as your last line. You'd get a mark for that. There is not enough evidence. Enough evidence to support the claim that the probability has increased. Or you can say the proportion. Okay? Because again, we're saying that anything above 1% is completely fine, our model's accurate. Okay? Now part C says, state the conclusion you would have reached if a 5% significance level has been used for the test. Okay. So if 5% was used, well 1.48% is less than 5%. So if we said that anything above 5% is fine, then that means everything below 5%, and what I'm saying is that 1% is really low, 1.48% is really low. There's not enough evidence, there's no way that the probability that the distribution is completely fine. The distribution must be wrong, it must be different, it must have increased. Okay? You would say reject H0 or whatever, so we would accept H1. That's weird, what is that? Okay. There is enough evidence to support the claim that the probability has increased. Okay? So I'm saving like the best question for last, or the most difficult question. But hopefully this is making sense so far. Okay, sounds like we're all good. Perfect. So, company produces pens. The probability that any pen is defective is 0.08. Sample of 15 pens is taken. Find the probability that 2 or more pens are defective. So, again, we can use a binomial distribution for this because either a pen is defective or it's not defective. And we know what the probability that it is defective is. So, sample of 15 and defective is 0.08. So what we're going to work out is the probability that x is greater than or equal to 2, which is the same as doing 1 minus the probability that x is less than or equal to 1. And again, we just whip out our calculator and use that. Put up CD, variable, we're looking for 1 out of a sample of 15. It's an 8% likelihood. So that gives me that number, but again, I'm going to do 1 minus it, so let's go back. 0.3403. Perfect, that's it. So, an employee claims that the probability that a pen is defective is more than 0.08. They take a sample of 20 pens and 3 are defective, stating your hypothesis clearly. Okay, so the null hypothesis is that nothing has changed. So the probability is indeed 0.08. The alternate hypothesis is that the employee is correct and that it's more than 0.08. So boom, 1 mark, done. Okay? Now in the sample of 20, so we have a sample of 20, 3 are defective. So what we're going to do is we're going to take the probability that x is greater than or equal to 3. Okay? The reason for that is if we're testing if the probability is increased, we want to work out the probability that there's more than that thing happening. So we're going to do 1 minus the probability that x is less than or equal to 2. So in these 5-mark questions, they're very quick, but the problem is that they're very tricky as well. So once you crack this, you will be able to score some pretty quick marks. So variable, we're going for 2. The sample size is now 20, and the probability, we again assuming that it stayed the same, and we get a number. And then if we do 1 minus that number, 0.2121. And we're looking at a 5% significance level. So this is the same as 21.21%, which is way bigger than 5%. What that means is we do not have enough evidence. There's a 1 in 5 chance that this probability is completely fine. So, yeah. All we need to do is write except H0 or there's not enough evidence to support the claim that the probability of a defect is greater than 0.2. And that's it. So you get a mark for doing this, a mark for the hypotheses, and you get 3 marks basically for the working out and writing all this down. It's pretty quick. It's not too bad at all. So again, we're going to start slowly speeding up to make sure this is all okay. Okay. Cool. Andy plays tennis. The probability that Andy would get one of his serves in the court is 60%. Andy serves 20 times. Find the probability that Andy gets exactly 15 serves in one court. So the first thing we're going to do is write out a binomial distribution. The sample size is 20. The probability that he gets in the court is 60%. So, for the probability that it's exactly 15, nice and easy, we're going to go straight to the probability distribution function on our calculator. So we're looking for 15 out of 20 and a probability of 0.6. 0.0746. I did technically say you should do 4 significant figures. To be honest, 4 decimal places is actually preferred, but we'll leave it like that for now. Part 2. More than 15 of the serves will be in court. Okay. Equal to 15. So, now we're going to go over to the cumulative distribution. And hopefully it's saved the stuff. Yep. Yeah, it saved the stuff for us, that's handy. And it's actually all fine, we can just get going straight away. So 0.949 blah blah blah. And we're doing 1 minus it anyway, that's why I didn't bother writing the whole thing. So there we have it. And again, I'm going to do it to 4 decimal places this time. So actually, I do significant figures again. Keep it consistent. There we are. Perfect. Okay. So, part B, this is where things get a bit more interesting. So I'm going to write this out first. So it's probably say it's changed, so now we're changing the sample size to 50 and 35 are in court. Now the null hypothesis, again, is just going to be the probability that it's equal to 0.6. But what would our alternate hypothesis be? It's asking us to test if it's changed. So you would think that it would be probability that's not equal to 0.6. And you would be 100% right. So, this is called a two-tailed test. Everything we've done up till now in terms of hypothesis testing has been a one-tailed test. Why? Because we've only tested if it's decreased or increased. With a two-tailed test, you test increase and decrease. The only effect this has on your answer is that if you have a sig level of 10%, you half it. That is the only impact it has. Other than that, you don't care. Okay? Hopefully that makes sense. The only way, again, what they could is then ask you to do another test where it's less than or greater than, and then you'll be able to kind of determine which one it is. But this test only tells you if the probability's changed. It doesn't tell you if it's gotten bigger or smaller. The other ones test if it's gotten bigger, right? Or smaller. Not, this one doesn't, it doesn't really test either, it just tests if it's changed, okay? So one-tailed tests are more useful, but the problem is that you don't always know if the probability's changed at all. So normally in real life we would do a two-tailed test, then we'd do, if we know that it's changed, we'll do a two one-tailed tests to test if it's bigger or smaller. Okay, so we do the same thing. So we're going to work out the probability that x is greater than or equal to 35. Technically speaking, you could also work out that it's less than or equal to 35 and do the exact same thing, okay? So you can work out either or, okay? But for this, I'm just going to do this way just because I want to. But you can do it whichever way you like, okay? So, 7. I'm going to test 34, almost but 35, out of 50 serves. Probability of 0.6. We get that, and then I'm going to go straight back to this, do 1 minus answer. We get 0.095, blah, 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 blah. So that's equal to 9.55%, which is bigger than 5%. So now you can see how they would screw you over, right? Because if we tested at a 10% significance level, we would have the exact opposite conclusion than if we tested at the 5%. So this is where you need to be careful. With a two-tailed test, you have to half the significance level. The reason for that is there's a 5% chance it's bigger, a 5% chance it's smaller, right? And if we did a overall 5%, it'd be 2.5% bigger, 2.5% smaller. That's all. That's also why it's two-tailed. It's either end. Okay? So there's not enough evidence. Whereas if you just compared it to 10%, you would say the exact opposite. There is not enough evidence to support the claim that the probability not has increased or changed or decreased, has changed just in general. Okay? Perfect. Next one. We have a probability of a biased dice landing on a 6 is 0.4, and it's going to be rolled 20 times. So, wait a sec. Okay. Just being wary of the time, it's probably best if we just go straight on to the exam question. So this is from the actual past papers. And again, so what you'll find is that one question will be hypothesis testing every single year. The difference is which probability distribution they give you. It could be normal or it could be binomial. Okay? But hypothesis testing comes up in literally every single exam paper. So you need to be aware of that, okay? You have to do this every year. Okay? So, let's do this. Using a suitable model for X. So this is what I mean by sometimes you need to decide what model you want to use. In this case, we're going to be using a binomial model, because either they dance, right? They're in the dance club, or they're not in the dance club. So, we have 36 students, and the probability of them being in dance club is 0.08. So this, again, nice and quick. The first part is worth 1 mark, the second is worth 2 marks. Just FYI. So we're going to use binomial PD because it's an exact value. You don't technically have to use PD. You can if you are very strange. You could actually work out, for example, less than equal to 4 and then also less than equal to 3 and subtract them, and it would give you the same answer. But that is a bit excessive. Okay. So, Jesus Christ, alright, 0.1674. So again, normally 4 decimal places is preferred, or, 4 significant figures. So this would be 1 minus probability that it's less than equal to 6. So 1 minus, and then actually we're just going to work this out all in one go, because we're amazing at maths. Binomial CD, variable, and what we're doing is changing it to 6. Okay, perfect, and then go back to thing, 1 minus answer. Cool. 0, 2, 2, 2. That's it. 3 marks. Pretty quick, pretty easy, not too bad. Now, for part C, it says only 40% of the university dance club members can dance the tango. Find the probability that a student is a member of the university dance club and can dance the tango. Tango. So, all you need to do is take 40% of 8%. So you're doing 0.4 times 0.08. The reason for that is they're saying and, right? 40% of the dance club members, so 40% of the people who are dance club members, which is 8% of people, can dance the tango. So you're working out 40% of 8%, which gives you 0.032. Nice. Lastly, a random sample of 50 students is taken from this university Find the probability that fewer than 3 of these students are members of the university dance club and can dance the tango. Well, we have, this is our probability, right? So all we need to do is, if we use, again, x modeled by 50 people, 0.032. So fewer than 3 people means that you're working out, so what I'll do is write this, but you're basically just working out to 2. Because again, we always have the less than equals to. 7, 1, variable, we've got 2, 50, and 0.032. You need 0.7851. That would be it. So hopefully you are okay with this kind of introduction to binomial distribution and hypothesis testing. This is basically everything you need to know. So I'd recommend just trying to get as much practice as humanly possible in terms of this. And other than that, if there are no questions, then I think we're free to stop.